Summary of this episode: the effect of sync on performance, Virga cloud, decision making, in-flight planning. Effect of sync on performance then. Notionally, figures then, Ash 25 falls at 0.7 of a knot and will produce a glide angle close to 60 to 1. When we fly into an additional amount of sync of just half a knot, then the glide performance drops to 35 to 1, which gives a 42% loss of performance. Our K13 then falls at 1.7 knots with a glide angle of 27 to 1. So certainly in flat air, it is left behind by the Ash. However, an additional sync of half a knot merely lowers its performance to 21 to 1. So it suffers only a 25% loss in performance. If we consider reduced sync then, the Ash falls at 0.7 of a knot, giving 60 to 1. If we end up with reduced sync of half a knot, then actually we end up with a glide angle of 210 to 1, which is nice. On a K13, similarly, has a reduced rate of sync and improves its glide angle to 37 to 1. But the real telling point is that we spend considerably more time of our time in sinking air than rising air in the glide. Visual sync. Do we know the structure of sync and what sync looks like? Should we take it in consideration during our routing? Well, we just looked and seen how badly even a high-performance machine is seriously affected by what we notional as very weak, almost insignificant sync. So yes, of course we need to take it into consideration. So, the important thing is firstly, sync has no vortex. It simply goes straight down. Because the evaporation of the water vapor takes place around the edges of the cloud first and from the center last, there is no formation of a descending vortex, and it lacks any kind of rigidity, unlike a rising thermal, which is the important difference. The exception to this rule is when there is precipitation. Rain, hail, or snow all generate a central flow of air like a column thermal in reverse. Why the higher the cloud base, the further between thermals? Well, the controlling force is the sync. Ignoring wave, there are three types of sync. Mass sync, subsidence, which we can largely ignore in the UK. The sync associated with the climbing vortexes themselves, and then finally the sync of the evaporated cloud, which make sync slugs. Remember that sync doesn't develop vortices. But on the left there, where the cloud base is low, as clouds evaporate, they make a small amount of sync, which falls down, cascades down onto the ground, disperses, and kills a small area off. Where the cloud base is higher, the sync cells are much bigger generally, so as they cascade down, they affect an area a little bit further away than the original cell, and certainly if they're lower, and so you end up with a spread out of the cumulus clouds. Structure of sync at its worst is like a waterfall and can even accelerate as it gets lower down. Otherwise, it's just like light rain. Can we sea sink? Well, we can, but often we don't look at it in that way. So the steam from kettles, as it evaporates, generates sink and it cascades down. And even sometimes from the power stations, you can see when the sky is not unstable. When it's stable or very stable, then you find that the steam from the power station cascades downwards. And to some extent, or a small extent, we can also see it at some bonfires as well, the smoke from the bonfires. Can we see it more clearly, more often? Well, yeah, we can, for example, here. And this is Virga cloud. It can be snow, hail, and we can see the ice crystals falling down and cascading downwards, but we can also see very clearly a wind shear here at height. So there is some form of inversion there. Snow is probably best because it falls slowly, and we can often saw the downward edges of snowstorms very effectively, and we can see both the rising and sinking air. Hail is not so good. It's very noisy when you fly into it as well. Here again we can see an unusual wind shear with the ice crystals cascading down. Bear in mind, if you couldn't see that sinking air, we might consider that the clouds are still looking quite active and quite good. In reality, of course, that's not true. Flying under them would be a considerable amount of sink. And in the very near foreground, just by the words Virga cloud to the right, we can see more of it cascading out of the sky there as well. Here we can see Virga cloud coming down, and again another much lower wind shear at height. As I suggest, it falls very much like water out of a waterfall, but here it is accelerating downwards, so then it becomes more of a ice cream cone shape, and the sink under there at the cone would be quite dramatic, to say the least. So here we can see the death and decay of a street. So normally we rattle along a street and use energy all the way up. Of course, at some stage that pogo stick's got to come back down again, and here we can see it very, very clearly. So in a way we could end up with a reverse thermal, which has happened a couple of times later in the evening, where you fly down between a sky like this, and you may well get certainly significantly reduced sink, or even a very gentle climb as you go down the middle between the two lines of sinking air. Seen from above, another quite dramatic picture of the decay of clouds. A very sharp wind shear in this one. Striations then are not Virga. So what we've looked at is we can see these striations, these lines coming out of the cloud at the bottom. And Virga will always display this. But sometimes when we're batting around the sky on a good day, we see these striations, these lines under the cloud and under cumulus cloud, and sometimes they can be good. Firstly, what's causing this lines of cloud climbing up? Well, it's not a change of pressure. It's not a change of temperature. It's a greater amount of humidity, which is condensing out. So it certainly may be a little bit cooler, but it's got more humidity in it at that point. And it's making these slightly wavy lines. Okay, so the thermal is carrying a higher level of humidity up. The lines are a little bit wavy. They tend to be a little bit wavy with some straightness, and they can really produce some very good thermals. And certainly you've got a video clip of that at some stage, which will be in this series, which shows this. The thing is, it can be humidity increased by falling precipitation, very similar to the Virga cloud pictures that you've seen before. Essentially, if they're purely straight lines, it's going to be bad. When looking out, what are you looking for? Well, certainly in basic training you're taught a lot about looking out for other aircraft and gliders, and of course that's absolutely valid, and it's air safety essential. Unfortunately though, we need to make sure that we don't concentrate purely on that aspect. Let's have a look then. We're in our thermal on a cross country, and we have a direction to go. So in this particular case, we're going in our direction to the left. We've decided that we're some 2,500 feet, 3,000 feet up. But we hit a thermal, and we're going to climb for 600 feet at 6 knots. We do 3 turns in 1 minute when we're turning quite hard and centered on this thermal. So actually, it's only going to take 3 turns to gain the 600 feet that we've stopped to climb. That gives us less than 10 seconds looking down the track on which we're going to make a plan. So here's our first turn, here's our second turn, here's our third turn, and now we're going to leave. So what are we looking out for on track? Well, other aircraft and gliders, of course, birds, and we need to read that sky. So clouds, amounts, any inversions, the cloud shadows, how much we're drifting. Key ground features to make our navigation very simple, so we roll out on the correct notional heading. There'll be a choice of routes. We need to pick the best route. We need to bear in mind airspace, thermal sources, or we might even consider field landable for when we're coming back this way or for a future cross-country in this direction. And we need to do all of this whilst thermaling efficiently. Can we really do all this? Well, priorities vary. When it comes to decision making, 80% of our performance depends on 20% of our decisions. Of course, a priority is usually to stay airborne. But leaving a thermal with no plan is wasting a lot of time. You'll be familiar with the term aviate, navigate, communicate, administrate. Power pilots, when they're flying cross-country, do hat checks. They make sure that their heading is correct, they're flying the correct speed, and they note what time it is. They plan accurately, fly accurately, and fly the plan. And it's called a work cycle whilst we're airborne. It identifies the priorities. If we can't fly an accurate heading, we're never going to get it. If we don't fly an accurate speed, then our planned time to be at certain points is going to be rubbish. So we check what time it is and check on the map where we should be. We look on the ground for the navigation features, and if we're early or late, left or right, we make corrections to our heading or speed to get back onto the plan. As a power pilot, rarely flies 45-degree angle of bank turns and rarely flies even a 360-degree turn. So the work cycle is very easy to accommodate. And of course, in gliding, you'll find invariably you are being taught to route via ground features. Yet gliding is about navigating around the sky. So for glider pilots, we do a hop routine. The glider pilot hop checks then. Heading, options, make a plan. The glider pilot has a general plan. He knows he wants to go from A to B, but he flies a rolling plan to achieve each short task. He wanders, detours where necessary. Note, if not using a visual feature, anticipate the heading on the nav system, because nav systems lag by about 40 degrees. The work cycle then, priorities. You have time and capacity on the cruise. So heading, orientation, where am I? Where am I trying to go to? Options, look at the ground and sky. Look for the climbs and link routes. Plan, you pick a block speed and takes the most efficient option with variable headings to stay airborne. The glider pilot has a rolling plan, flying from B to C, beyond the next thermal, but also plan D, that you actually might have to land somewhere that wasn't in the original plan. That's if it all fails. And you must always have a clear plan about where you might have to land. Summary. Effective sync-on performance, Virga Cloud, decision-making, in-flight planning.